Okay, so in this video, I just wanted to recap a few things that we mentioned when we met on Friday, and that's recapping pH before we go any further. But the main thing that I at least wanted us to make sure that we understood was dealing with these protons and what they mean to us in terms of pH and how you should be thinking about pH. So basically the key thing that I need you to know is that when you think of protons, we were talking about those hydrogen ions. So the H plus charge is the key thing on that. So when we're going through like how acidic or how basic something is, yeah, it's going to be with that number range, but the biggest thing is you to conceptualize what does pH really look like. So like I just mentioned the other day, that hydrogen ion, that's what we would actually call a proton. And that's only when it has that hydrogen charge. And that's something that I think is really, really important for you guys. So basically what you should think about when we go over pH is this, is that if I increase my, actually let me rewrite this. If I increase my hydrogen ion, I'm actually decreasing the pH, and vice versa. If I decrease my hydrogen ion, I'm actually increasing the pH. So it's actually this inverse relationship when you think of hydrogen ions. So the more hydrogen ions there are, the lower the pH is going to become. So it's a really simple inverse relationship to remember. So in this case, if I added more of those hydrogen ions, I'm actually lowering the pH. And I can even add more hydrogen ions and I'm lowering the pH even more. So if we looked at something in terms of increasing acidity, this would be the lowest. This would have a relatively low pH. This one would have a relatively, excuse me, I had that reversed. This would have a high pH. This would have a low pH. Yeah, and myself included, look out for that. The more protons you have, the lower the pH, and vice versa. So, and that's something that they'll trick you if they label this on a test like A, B, and C. And if it asked, hey, what has the highest pH? And again, keyword there is the highest pH. It would actually be choice A. So just remember, more of those hydrogen ions, the lower the pH. So make sure that that really is embedded with you guys. So, and the reason why is just because like we'll talk about things like cell respiration, and this is a mitochondria, and part of what makes the mitochondria so efficient is how much of those protons they have. So it's just going to make your life a little easier in the long run. Now, the main thing that I needed to mention in this video is reviewing a little bit of equilibrium, and really making sure that you guys remembered what it means when I say a reaction shifts to the right or shifts to the left, or shifts to make more product, or shifts to make more of your reactant. So basically we got to review this, which is called Le Chatelier's principle. And that states that a reaction is going to shift to reverse whatever change was applied to it. So whatever that stress is. So going through one example, let's say if I had this made up equation and I talked about increasing A. I'm saying that I'm increasing the concentration of A. And the question would be, which direction does the reaction shift? Well, I'm adding more reactant, and I need to reverse that stress. So I'm going to actually shift to the right, or what's known as shifting to make more product. So hopefully it's just reversing whatever stress you're added. So if I increase my amount of A, I have to shift to make more of my product, C and D. So that's what we're talking about when we think of equilibrium with Le Chatelier's. Now it can also be asking you in forms of this, what if I lowered my amount? I actually decreased my amount of A. Well, the reaction would have to shift back to replenish what was removed. So taking that away, the reaction shifts to remake what was removed. So that's what Le Chatelier's principle looks like. And you'll see it in things like photosynthesis, for example. What if I increase my amount of CO2 or increase my amount of water? Well, I actually have to shift to the right to make more of my product. So it's a relatively easy concept, but I did want to make sure we revisited that before we get into what's called buffers. So, and feel free to reach out if you want any extra videos or resources on that. We're not going to be messing around with gases or pressures. It's just if I increase something, which way is it going to shift? Or if I take something away, which way is it going to shift? So that was what I wanted to point out there. So that leads into the main thing that I needed to mention here in this video, and that's buffers. So buffers aren't too complicated, at least with what we have to talk about here. But the key thing of what buffers do is they maintain pH, meaning you don't want your pHs to change, especially in the body. So like I have it written down here, not something you have to memorize, but we like to have our blood at a pH of about 7.4. And you don't want that to go too high or too low, because some really catastrophic things can start happening metabolically, meaning reactions stop working, you aren't making protein, you aren't doing things that you're supposed to if your pH changes too much. But we have buffers. And what buffers do is they just literally help resist a pH change. So if you look down here, and you don't have to memorize this right now, but it's basically a series of steps. It's a steps of reactions that help address, okay, where can I donate protons if needed? Where can I accept them when needed? So all buffers, they have to be able to do these two things. Now, it just means that sometimes you have to form a molecule that can donate protons, or they have to be able to accept them when they're depleted. So that's what buffers do. So let me just put this into context in this equation. And this is a pretty common one that we'll talk about. This equation right here is found in our blood. And that's because you don't want your blood pH to change. Like I just mentioned, it's about 7.4. You want to keep it around there. So again, this is just kind of stating the same thing. It helps allow our reaction to proceed in either direction, whether you can go forward or reversed to restore the appropriate pH level. In simple terms, it's a reaction that can remove excess protons. And that to me is still, that definition that I'm trying to give you guys is like, don't let this become more complicated than it already is. Just understand that what a buffer does is it helps resist a pH change. And in simple terms, like mechanically, what is it doing? There has to be a way to accept or produce more of those protons, okay? So let me go through this example using that Le Chatelier's or that equilibrium review and make sure you guys are kind of caught up to speed on that. So here's the equation, and I'll kind of use this as my talking point. I just want to go back here and remind you what's up with the protons. If you increase the protons, you're actually going to be decreasing the pH, and vice versa. If you decrease the protons, you're going to be increasing the pH. So that is kind of the key thing that you need to remember. So here's where I want to go ahead and go through a couple of practice ones and make sure you guys are all caught up to speed. I'm going to actually go ahead and delete that note. So here's where I'll kind of start off with this. What if I gave you the scenario and I asked you, what happens if I increased, let's say I'll increase the concentration of CO2. Okay. And all of this relates to the pH. I want you to try to follow along and say, okay, well, what happens if I increase CO2? And by the way, just don't forget those little brackets remind you of that stands for concentration. So let's look at our equation up here. I'm basically saying, well, what if I increased my CO2? Well, if I increased that, right, I'm adding a lot of CO2. I'm increasing my reactant. And I were to ask you, well, what direction is that going to shift to? Well, hopefully you're able to catch on now that if we increase CO2, it's going to shift to the right. And what that's going to do is help form this molecule called carbonic acid. And that's something that we'll talk about quite a bit as well. But just for now, know that, okay, it's shifting to the right and it's forming some carbonic acid. So cool, it's shifting to the right. That's good. That's what I want you to at least understand. If I increase CO2, I'm shifting my reaction to the right, and that's important. Because now all of a sudden I'm actually increasing this H2CO3, that carbonic acid, which is going to cause the reaction to shift to the right, and I'm going to form protons. So I'm actually increasing my proton concentration. So if I set it up this way, if I increased CO2, I actually am increasing my protons, which really means I'm lowering the pH. So if this question was asking you guys, well, what happens if we had a decrease? Well, let me take a step back. Just follow through and let's recap the steps, right? If I called this like step one was to increase my CO2. That caused my reaction to shift to the left, to the right. I formed carbonic acid. Carbonic acid shifted to the right, and I formed more of those free protons. And again, as I just mentioned earlier in this video, if I increased those protons, I lowered the pH. So that was the key component to that. And that's an example of a buffer. So let me kind of go back and just help clarify that one. I'll do another example. So let's do the same setup. What if you, let's say, what if the pH gets too low, right? Let's say we're not talking about the ocean or anything like that. Let's talk about what if you decreased CO2? What is that going to do to the pH, right? So in this case, I'm asking, okay, well, instead of increasing CO2, I'm actually going to be lowering it. So that concentration of CO2 is going down. So all of these things are going to actually be shifting to the left, to the left. So you need to think about it from the context of, okay, well, what's happening to my protons? I'm actually having less of those protons available. So I want you to now understand that if I decrease CO2, if this was the question, if I'm taking it away, everything is shifting to the left. I'm having to reform that CO2 that's being taken away. But look at what's happening to your hydrogen ions. I'm getting all of those free floating hydrogen ions are getting used up. So I'm actually just ask yourself, well, what's happening to the hydrogen ions? In this case, the concentration of the hydrogen ions, I put brackets around it to represent concentration. The concentration of those hydrogen ions are going down, which really means that the pH is going up. So that's something that's pretty important, right? So just kind of be able to follow through. And this isn't something you have to memorize by any means, but you do have to be able to understand it in terms of the hydrogen ions and shifting to the right, shifting to the left. And so, for example, this is important. If you don't exhale, your pH is going to actually start to go up because your CO2 levels go high. And that's where you can get some really catastrophic biochemical reactions that shouldn't happen, or they won't happen at all. And that's just as problematic. So CO2 matters big time. And in terms of your CO2 in your blood, that helps with pH balance as well. So that's what a buffer is. And again, it's just like I mentioned in the previous example, you have to have something that can accept a proton when needed and donate that proton when they're depleted as well. So having that carbonic acid is a key player in all of this. So really, really cool that you guys have that metabolically. So it's crazy. So moving forward, the last thing that I wanted to mention is taking that same equation and kind of relating it to ocean acidification. So basically, if you look over here on the top right, it's not just airplanes, but basically we're getting to this point where we're increasing our CO2 input into the atmosphere. And this equation happens everywhere. That carbonic acid, if you look over here, in the water, in the ocean, if you increase CO2, you're actually going to be increasing your carbonic acid. If you increase that carbonic acid, like I just mentioned here, right, you shift it to the right, shift it to the right, you're increasing the protons. Now, you guys all know now, if you actually are increasing, you're increasing your protons, so you're actually lowering the pH. So by adding that CO2 into the atmosphere, you're actually forming an acidic water source. And so that's a problem. You have a lower pH in the water. And not only that, one of the bigger reasons is because of this, what I just circled here at the bottom, this carbonate ion. So I'll say that that carbonate ion is needed for marine life. More specifically, it can bond to calcium. Those two, that carbonate ion and the calcium ions bond together. And you see that a lot in exoskeletons or shells of different marine life specimens and species. So having calcium binding to that carbonate is important. So why does ocean acidification matter as well? And that kind of leads into this. The less of that carbonate ion available, it's going to be less of that calcium carbonate can be used for marine life. So not only are you making the water acidic, the bigger contributing factor is that there's less of that calcium carbonate needed for marine organisms. Excuse me. And if that starts to deplete, we'll get into ecology later throughout the year, but once you affect one level, it can cause some really big complicated issues in various ecosystems. So that's something that's super important for us. So we're kind of taking that idea of buffers, pH, kind of putting it all together in one example. So like this is just another picture. Having that CO2, you're actually increasing that carbonic acid. You're forming more of those protons. And again, this right here is what's actually lowering the pH right there. Not only that, it grabs all that excess CO3, right? That carbonate ion, and this can't happen. So you're not able to actually form those bicarbonate ions, the more of those protons that you're putting in. And that's one of the bigger issues with this ocean acidification. So cool. The last thing I needed to mention with this one was molarity. And we'll talk about it in this class. You're not going to have to calculate it, but the bare minimum that I expect you to at least be able to understand is right down here, which is going to be the definition. And it's pretty easy. It's just this. The higher the concentrate, the more concentrated it is, the higher that molarity value is going to be. So we're going to be looking at things like sugar solutions and how that impacts things like osmosis, how much water is uptaken by cells. So don't let the calculation side freak you out. A lot of this is just based on molarity. And so we'll talk about things like solute. Solute is what's getting dissolved. Solvent is what's doing the dissolving. Most of the time, it'll be water in this class, but I've seen the AP test throw out things like, oil as being the solvent. So let me just go back and show you this. It's really, really simple. This just shows you that, okay, I have copper sulfate. That's my solute. This is all water here. And this is giving me my molarity. So just the bare minimum, understand this, and I'll be satisfied. If I add more of my solutes, look what's happening to my molarity. It's going up. So less solutes, lower molarity. If I added more of the solutes, it's a more concentrated solution. So that's it in terms of the chemistry in the chapter 2 review. I just wanted to cover that. Reach out if you got any questions. We'll see you guys in the next one.